thank you all for coming out here. Before we get started, just a brief disclaimer. So there's a couple spots in this presentation where we've stripped the license text off the top of some blocks of code to make it easier to read the code on the slide. In all those cases, unless there's an explicit license text at the top of the file, it's all Apache 2, copyright the Kubernetes authors. All right, so I'm Solly Ross, and this is Phil Wittrock, and we want to do a quick survey. So how many of you have written your own controller or operator? All right, keep your hands up. Only put them down if you have not copied and pasted from an existing controller to get started. Ah, an impressive number of you, but there's still a lot of you with your hands up. So we were wondering, Phil and I, at one point, why are we copying and pasting so much? So for those of you who are not as familiar, controllers are one of the basic building blocks of Kubernetes. So Kubernetes APIs are not imperative, they're declarative. They just store state. Very simple. The controllers are the loops that actually check for changes to those objects, that state, and check the real world and figure out the difference and fix it. So hypothetically, a controller should be pretty simple. We watch some resources, we do some business logic, we reconcile the differences between the real world and the desired state, and we have a little bit of plumbing to wire things together, right? How complicated could it be? So as developers, probably one of the first things that we do when we start in a new environment, if we say want to write a controller, is we look for a sample, right? And there is a sample controller for Kubernetes, k8s.io/sample controller. So let's take a look at that. So if we look at the main file of the sample controller, controller.go, we can see that it's 429 lines long. And if we take a look at the rest of sample controller, not even including the vendor directory, we can see that there's 28 directories and 52 files, which seems rather large and cumbersome for a sample, but maybe it's all just comments. So let's take a look. Maybe if we just rotate that a little bit. Perfect. So that's simple, right? You guys can all read and understand that perfectly. So another quick survey, show of hands. How much do you think this is boilerplate plumbing? Raise your hands if you think it's like a quarter plumbing. Raise your hands if you think it's half plumbing. All right, let's take a look. Everything in red is boilerplate. Everything. Lisa has good comments, though, that are clearly understandable if you've never written a controller before. So you guys couldn't read that, and I couldn't read that. But thankfully, Phil went and did some work ahead of time, and he has prepared an overview of what that sample controller does for us. So let's take a look at it. So the first thing we do is we copy clients into a reconciler struct. Then we create a queue for reconcile requests. And then we add event handlers for all the object types, like our custom resources and our deployments that we're interested in. But we don't enqueue deletion events on the reconciled type.
Well, unless you're doing finalizers, because then you need them.
I forgot about that. All right, so unless we have a finalizer. But we do enqueue deletion events for own types.
But you got to walk the ownership relationship on that one.
That's right. Let's look at the owner references, walk them up to find the parents. And we need to be sure to handle tombstones, which is what happens when we think we miss a deletion event.
I don't think we actually need to do that anymore.
That must have changed recently. So then once we have all that, we have to write logic to turn our objects into keys that we can add to the queue and typecast those requests into a string and do error handling if for some reason we can't typecast those requests into a string. And then we start some worker threads, but not too many worker threads. And then we start some informers, and we wait for our caches to sync. And I think we probably should be done at that point.
Yeah, I think there's just a couple more items, actually. There's, of course, you got to do management of the queue, popping items, and all that sort of stuff.
Right.
You got to do error handling for that. You have to use rate limiting, obviously. And then don't forget to forget the thing when you're done.
Don't do it for transient errors.
This is correct. Then you got to go ahead and reconcile the object. So when you do that, you got to take that string and split out the name and namespace and error handling, whatnot for that. You got to set up the signal handlers for the binary, right?
I think we're about done, right?
We're about done, as long as you got Unix and Windows and everything else.
All right, we're done now, though.
Yeah, after you generate the clients, you're done, except for the listers.
OK, cool. So clearly, very, very, very simple. And lest you all think that this is just limited to the sample controller, another quick quiz for you all to think about in your heads. One of these is a sample controller. One of them is a built-in Kubernetes controller. And one of them is a third-party operator for a popular database. And all that red, that's all boilerplate. So as you can see, they all have a lot of boilerplate. So let's break that down into numbers. I like numbers. 65% of that code is boilerplate. So that's copy and pasted functions, basic wiring with some weird nitty-gritty details, and initialization of dependencies. So what do we do when we have a bunch of code that we're repeating over and over again? We put in a library. And when that code is used across all of our projects and becomes the de facto library, we call it a standard library. So we talked to the Go core maintainers, and we got them to put a standard library for controllers in Go 1.12, which you can just import as controllers. Just kidding. But seriously, though, we wrote a library, a standard library even, for writing controllers, and it's called controller-runtime. So let's take a look at how controller-runtime has captured some of this boilerplate, some of these patterns, and has refactored it out into reusable chunks that can make it easier for you to build a controller.
Yeah, so the first thing you're going to want to do when you're creating a controller is create a controller. And so over on the right, what you see is the controller runtime version of creating a controller, which basically says, just set one up for me and start it. Here's the signal handler to use. On the left, you have the sample controller version of the same thing, which is manually instantiating queues and setting up various machinery to get started. The next thing you're going to want to do is declare that you are interested in a particular object to reconcile. And that means that you need to be triggered when there are changes for that object. And so here on the right side, what we have is highlighted in yellow the additional code to say I want to reconcile for changes to type foo. And you'll notice one part on the top has a nice little function to inject a client. And what this allows us to do is do some very, very lightweight dependency injection for controllers to declare the sort of dependencies they need and let those common pieces be provided to the controllers. And on the left, you saw, of course, the alternative. OK, so here what we have is the next thing you probably want to do is if you're writing a controller, oftentimes you are creating new objects. And you need to be notified when there are events on those objects, such as they are deleted or something happens to them. And so you say, I want to reconcile my foo when the things it creates or manages change. And so on the right, we have you declare, hey, I own these sorts of things. And so go ahead and trigger the owner when they change. And on the left-hand side, you have the bespoke way of cobbling all that together with event handlers and whatnot.
So this looks all great and awesome, Phil, and it looks like it's really easy to get started. But I have a problem with libraries sometimes. And that is, I sometimes like to do crazy, complicated stuff. And sometimes I get to a library, and it's great for getting started. And then I go to do my crazy, complicated stuff, and the library won't let me do it. The abstractions it provides don't allow me to do the things I want to do, and I have to rip all that nice, easy stuff out and just go back to the raw underlying cumbersome stuff. So how does this handle that?
Yes, that problem makes me cry, Solly. This is the third iteration of us trying to solve this problem. The first iteration we started 2 years ago was something called API Server Builder. And there we looked at all the boilerplate code and we say, you don't need to hand copy that and write it. We'll just code generate it for you because we're generating so much code anyway. And so we did that for a while, and then we looked at it again kind of sideways. We're like, why are we generating that? Why don't we just make it a library? So that's what we did. And the first iteration of KubeBuilder, I think pre 1.0, we put together a library that looked very similar to the builder pattern that we demonstrated earlier. But the problem was that library called directly the underlying API machinery. And so as soon as you wanted to do something that the builder didn't support, you were back to the bad old days of cobbling it together yourself. So when we redesigned for the controller-runtime library in KubeBuilder 1.0, we rethought this and said, you know what we really need is layers. And you should be able to break through these layers and do more and more complex things while still having abstractions on top of some of the stuff API machinery has provided. And so we start out at the top of the pyramid with a very simple pattern that satisfies what most people want to do, especially in their first few weeks of work, right? Which is listen to a couple different resources, create resources, and reconcile them. And as you do more complex things, we provide a set of built-in, more flexible components that you can use instead of these and provide a little more details and compose together. And underneath that, we have an extension layer where you can go and implement your own versions of interfaces to really extend the platform to do new things. And then underneath that, we have API machinery. And our hope is that if we've done our job well, API machinery is really only for arcane sorts of actions such as transmutation or something like that, and you never have to actually go use it. So what I'm showing here is that second layer underneath the pinnacle of the pyramid. What happens when you break out? This is an example of that for type function. But in this case, what we're doing is we're providing a source, and we're saying the source for a set of events is look at this pod. And the action to trigger for those events is to go ahead and queue that particular object. Here at that same layer is the owns relationship represented. And this one actually allows a little more functionality. You can say control whether do I care if it's a controller or not, and then compose these pieces together to use, again, that same source on a different type with a different event. This one you haven't seen yet. Because this is not so simple it belongs in the simplest use case, but is still relatively common. Right? And frequently we'll have people come to us with scenarios such as, hey, I wrote this thing that needs to trigger an event when a config map changes for some pods. Right? The deployment has a reference to a config map gets updated, now I want to do something. That's not an owns relationship. That's this bespoke relationship that the user kind of defines, even though that one is actually a little more common. And so we allow you to provide a mapping function to say, given this object, map it to another set of objects. And this has access to a client, so you can even look up from the cache particular indexes or various things like that. Another common use case is actually we have something that needs to be triggered whenever a node is added or removed to a cluster, and scaled or something like that. So we do see these arbitrary relationships happen. But we still don't want to make you go all the way back to API machinery if you're like, you know what, I do have something a little more bespoke than that. And so those pieces we pass in are actually interfaces. There's a source that's an interface, and then there's an event handler that's an interface. And so you can swap out the source to be something like a pub/sub event source or a webhook event source if you were to implement that.
Or maybe even listening from Slack. Trigger things on Slack commands.
Perfect. And And then you can also implement your own event handlers and say, OK, I got this event. Now what do I do with it for the queue? In theory, you shouldn't need to actually write your own event handler. The mapping function is actually pretty flexible. But we designed it this way because we know that we're not going to know ahead of time all these cases people are going to encounter. And so we want to provide that flexibility. So I'm going to say, don't use this.
The common cases should be easy, and the uncommon cases should be possible. So what does this get us, right? So it makes it really easy to get started. It makes it easy for us to build what we want. But what does it get us in the long term? Well, for developers, in addition to getting started easily, we get the ability to pull in new features, performance improvements, without having to rewrite all of our code. So here you see a PR that actually introduced some performance improvements through shared caches to the core Kubernetes controllers. And this was a Herculean effort that ended up touching 151 files across the Kubernetes codebase, and had to be, a bunch of them were just changes by hand. And we don't want that to happen. And with something like controller-runtime, that doesn't have to happen, because none of these changes were changes to the business logic of the controllers. They were all changes to underlying implementation details. But once we move beyond kind of the getting started, adding new features, move to like day 2 operations, things get even more interesting. For ops and SRE, we get standard observability and behavior. So we can monitor all of our controllers in similar ways. We can write a baseline set of dashboards and alerting. We can look at logs for any controller and have a general idea of what's going on. And when we need to do maintenance because we found a bug, again, it's just an update of a dependency as opposed to a rewiring of all of our code. Beyond that, we get a stable base layer for people to build on top of. Instead of reinventing the wheel, people can build up on controller runtime. So you get projects like KubeBuilder and Operator SDK, which helps you get started writing your operators and controllers. And they didn't have to reinvent everything from scratch. And we can both focus on writing the best possible abstractions over API machinery.
And one thing that we didn't plan for, but we've actually found, is that different folks discovering the controller runtime in KubeBuilder say, hey, this is pretty cool, and we like the top end of this pyramid. But for this specific domain, we could actually build even a higher layer on top of that pyramid, right? So for instance, if it's stateful applications, they may have some set of lifecycle hooks that an operator would, every operator should implement, right? Or if it's Kubernetes control plane operators, for instance, and manage the control plane itself, there's a set of hooks there. And so we're seeing, because we're seeing a number of different domains with people interested in this, what we're planning on doing moving forward is to actually work with these folks to develop that higher level on the pyramid, right? And then that way we make sure that across different platforms that get built on top of KubeBuilder, there's still a nice standard mechanism for breaking glass out of that top level of the pyramid into lower level pyramids, and standard ways of approaching and building domain-specific operator platforms.
And those folks get to focus on building awesome stuff, and they don't have to deal with the nitty-gritty arcane API machinery. So let's tie this all back together. You remember this from before? This is our sample controller. I lied a little bit. I actually forgot to tell you about this piece too. That's the main file. It wires up clients and pulls in flags and loads tokens for talking to the cluster. So there was more. So if we look at what this looks like in controller runtime, it fits on the slide. It's almost readable at this size. So there's 3 parts here. The first part is basically the entirety of that main file. It just loads up and declares what we want to do. Second part is our business logic, and that third part over there on the edge is just the structure for our deployment that we wanted to create, because that's what the sample controller does. It creates deployments. So in conclusion, controllers can be simple, and we don't need to copy and paste as much if we think about, when we find ourselves copying and pasting, what our abstractions should be. And we think about how we can refactor those out into reusable building blocks that are flexible enough to let us get our work done, but simple enough so that we can understand them easily. Any questions?
That was actually a joke I put on there.
All right, so
So how does KubeBuilder compare to the operator SDK?
okay, so KubeBuilder and Operator SDK are kind of two sides of the same coin. They have a little bit of a different focus, but they still use the same underlying libraries. So they scaffold out your initial project differently, but they use the same underlying mechanics. They both use controller-runtime.
Yeah, I can add a little bit to that too. So originally, these were built independently. KubeBuilder pre 1.0 and the Operator SDK. And they both did not, neither one looked like that pyramid we showed you, right? It was like just API machinery and then one layer on top of it. And both of us looked at, both projects looked at what the other project had done and said, hey, there's actually some cool stuff in there I hadn't thought about, and I would like to copy that. And then my project will look just like yours with a couple more features, but you'll copy mine, and then our projects will look the same, but have incompatible interfaces, right? And so we got together and we said, hey, what if we just thought about this a little more and came together and built out a shared library, and that is where controller-runtime came from. And so both Operator SDK and KubeBuilder use controller-runtime as their base, and so that means if you end up going down the road with one, you actually are not totally locked into it if you're mainly interacting with controller-runtime library.
And it also means that if we get libraries that are designed to provide additional functionality that are built on top of those controller-runtime primitives, they work in both Operator SDK projects and KubeBuilder projects.
And they differ, and then the projects differ in certain ways, such as opinions about, hey, what does the default project structure look like? Or how should we scaffold out files for you, right? That sort of thing.
Is that enough of a difference to have two different tracks in the story? Because it's going to be confusing for adoption.
That's an excellent question. We should probably touch base. I don't think we've done that recently.
Yeah, what was the question?
Sorry, the question was the differences around scaffolding and the way the projects are different. Is that enough to justify the end user confusion, and every time we give a talk about KubeBuilder, someone asking us what the difference between that and Operator SDK is? Yeah.
What about other languages? Because KubeBuilder and KubeBuilder SDK is both based on internal runtime. Internal runtime is using Go, but when you think about it, it's just making requests against the API server, so it's just this relative socket, right? So the same way that I know that there is a project, but I think it's called named Kubernetes Client SDK, that exists for several languages such as Python, Java, JavaScript, and others. Would you think that in the near future we would have something similar to container runtime, but for other languages than Go?
Maybe. So one way of doing this is not to generate controller runtime for every language, and it's to expose a webhook-based approach, for instance. And so there's a project called MetaController that takes that approach. That is probably the more likely direction I see the language agnostic approach taking, and kind of is in theme with the as you have more and more specific things, you actually have get funneled into a more specific route. And so if you're doing something where that's good enough for you with the what the webhook model supports, go for it. Then when you actually find out you need some piece that happens to be written only in Go do that. I'd be also interested in seeing other folks maybe copying our APIs or approach, importing it to other languages. That would be interesting to me as well.
It turns out maintaining a bunch of libraries across all the languages that everybody wants to use is a big problem. Like, it takes a lot of people, and it takes a lot of people who are good at the individual languages, right? One of the things that's important in any project like this is that the code should feel idiomatic. So if you just, if you tried to have someone who didn't say no Python very well, just knew the surface, kind of write controller runtime in Python, it might come out more cumbersome. So it's also a maintenance problem.
And the question was, can we have this in all the languages, I think.
To what extent, like are the test fakes and harnesses for common test cases supported by Kubernetes?
So the question is, to what extent are the test fakes and common test harnesses for common use cases supported by KubeBuilder? So we do have some fakes for a lot of our stuff. One of the things that we've found out during testing KubeBuilder itself and kind of the KubeBuilder maintainers when we wrote controllers ourselves before we wrote KubeBuilder is that it turns out eventually you end up with a test fake that just kind of looks like the API server, but like missing a bunch of features and maybe with some more bugs in it. And so the approach that we encourage instead is we make it really, really, really easy to just have your test harness run just the Kubernetes API server.
And etcd.
And etcd, of course, because you need etcd. And so like all of the controller runtime internal tests, almost all of them do this, and all of the stuff scaffolded out with KubeBuilder does this as well. You just call setup my test environment in your kind of before suite, and it stands up an API server that you can talk to. And this, we found out, works really well because you get a real API server that behaves exactly like the real API server would, and it makes it really easy for you to actually focus on writing your tests as opposed to writing many, many lines of boilerplate, I'm going to pretend to be an API server code.
And we are interested in making this actively better. The different things that are on the list are looking more closely at EDE tests and how do we make EDE tests easier, and more guidance around what should go in an EDE test, what should go into like a local EDE test, if you will, or integration test, or whatever you want to call it. Making those local tests that spin up the API server to be a little more user-friendly, and like, for instance, possibly vendor API server as libraries instead of as binaries. So there's a lot of stuff that's interesting to work on in that area.
Any other questions? I think there's a few folks behind the pillar, but I can't tell if they're raising their hands. So just like shout if you're raising your hand.
Do you come across any necessary performance trades imposed by these abstractions?
We have not. We've not done super extensive performance testing, but we have written a number of kind of real-world controllers that have been using controller runtime pretty successfully. It is one of the things on our list, kind of things that we would like to do, going through and doing more extensive performance profiling, but we expect that the impact should not be terrible. And,
Yeah.
and we've thought about that a bit as we're designing. And of course, there are always trade-offs.
PR is welcome. Yeah, I mean, and we have looked at it. Like, one thing we've done is if you take the long code you saw originally that was red with the spiky stuff, like, we refactored that and massaged it. Like, we didn't just start over and say we're going to write something else. It's like, okay, how do we pull that into a library? How do we pull that into a library? So in most areas, we don't expect there to be huge performance changes because all we did is like factor stuff out into a library. There are a couple places where we did do stuff that was kind of novel, which is in the client. And we do a bit of reflection in there in a couple places. So that would be probably one area to look at. One possible performance improvement that we would see is the client is very friendly towards reading from the cache. In the old sample controller way, you have a lister and you have, which is separate from your client, and so engineers have to make sure they get the programming right to read from the cache separately from the API server. And so by getting that sort of simple integration, you might save yourself a bug that would cause worse performance.
Ideally, so the question was, if I do things this way, how much of my code is typecasting? And the answer is, ideally, none. We have attempted to write things in a way that either do not require typecasting, or we abstract away the typecasting from you in a way that we attempt to actually do some checks. So like the way our client works, we have what's closer to a dynamic client, except that you pass in a concrete struct, and we use the type of that struct to look up what we're supposed to fetch. Right? So if you pass in a pod object, you're guaranteed to get a populated pod object. Same thing with if you look at the reconcile key. So in traditional handwritten controllers, especially those in core Kubernetes, they take a key in as a string, and then you have to manually split that into namespace and name, and you hope you do it right. Otherwise, you'll get errors. In controller runtime, we pass you in a pre-split key in a struct, so that you just have a struct with namespace and name, and you don't have to typecast.
So our system is using Golang reflection.
Say that again?
Are you using reflection?
We are using some reflection under the hood, especially in the client. A lot of the Kubernetes API machinery actually uses reflection under the hood.
We did not like totally just introduce reflection where there was like no reflection before. We used the same sort of reflection that already existed actually in the libraries, but maybe applied it in a couple additional places or a little bit differently.
How many of the core cube controllers are using the controller runtime?
So none of the core cube controllers are using the controller runtime right now. For various, probably mostly non-technical reasons. It would be super awesome if eventually we could get this to the point where the core controllers were also using controller runtime. But for the moment, we are looking at mostly just third-party controllers and also kind of supporting gradual refactoring. So if you want to do stuff like you're writing a new cloud controller and you want to run some of the cloud controllers from core Kubernetes plus some of the stuff you wrote yourself with controller runtime, you can do that and run them in the same controller manager binary.
I'd like to add something to that, which is like part of your question might be like, is the project being built with this, right? And to what extent is it? And like the Kubernetes as a project is probably moving towards a direction of more components, more independence of these components. And so as that happens, we see those projects running on controller runtime. So one example is the cluster API uses controller runtime, and that's because it was started outside of Kubernetes repo and had a fresh start. Taking, like, for instance, these very complicated deployment controller, right? Each of which was copy and pasted and changed a little bit here and there. That would be like a pretty big endeavor, I think, and not clear that we would see, not clear that it's the best investment of our time right now.
It's doable, and it may happen eventually, but right now we're focused on making the path awesome for stuff that kind of lives outside of the core Kubernetes controller manager binary.
All right, just 2 more minutes.
So what the KubeBuilder says is for things defined by CRDs. I have custom resources defined by Golang.
So your custom, it uses, like, your custom resources are defined in terms of Golang types. And you can also, like, KubeBuilder is designed from the perspective, like the scaffold that it sets up is, I have some Golang types, I want to turn those into a custom resource definition so I can use them as custom resources on the cluster, and I want to reconcile them. But you can also use built-in types as well with controller runtime, like deployment and stuff.
Those types are CRDs. That's how they're reflected on the Kubernetes cluster is CRDs are generated from the Go types. Yeah, I mean, if it's working.
Let's talk a little bit after. All right, I think we're out of time, but thank you all for coming and hope you had a good time.